Next, I'd like to welcome Mario Morgado. He's the Director of Innovation at Cytognos, and he's going to pose the question, automated data analysis and flow cytometry, a clinical only option? So you can go ahead and share your slides, Mario.
Okay.
That looks good.
Yep. Can you see my presentation? Is okay? Okay. Thank you very much for the opportunity to participate in this meeting. And after the previous presentation, it will be difficult to be in the same level. So more than trying to talk about a specific product from our company, I would like to raise a question about the need for automated analysis tools for the new generation of flow cytometers with a lot of new parameters like the spectral ones. So, as you may know, Cytognos is the developer of Infinisight, which is a flow cytometry data analysis software mostly focused on standardized clinical application, but not limited to that. It's only known for that. But with a unique set of tools that can be useful also for more basic research applications for outside of the clinics. Independently on the tool you like the most for your data analysis, whether a commercial software or R-based algorithms or whatever you like, usually, and assuming that our data is correctly compensated and mixed, we can divide the process into several steps that starts with clustering process or a gating process, whatever you like, to create groups of events, and then label those events based on their phenotype, do some kind of statistical analysis, enumeration of different subsets, do an interpretation about the findings of that analysis, and then reporting the results. And this process of creating groups of events and then labeling them according to the phenotype is probably one of the things that makes Infinisight different from most of the other commercial softwares around there when we talk about manual analysis. In Infinisight, instead of creating a gating strategy with all the gates permanently visible, the user goes through a process of discovering event subsets or population subsets, in which each subset is defined by a unique sequence of logical gates. Those gates are not shared by other subsets, like when we do fixed gates for example, CD4 that we can use for monocytes and CD4 T cells. So in Infinisight, you don't do that. You cannot share gates within subpopulations. And another thing is that they are not usually visible in the software unless the user toggles them on. So once you create a population, once you label the population, those gates disappear. They are not lost, of course. You can toggle them on, but they are not always visible. However, the complete set of gates you create to do these clustering, these grouping of events can actually be saved as an analysis strategy, and you can reuse them. So you can apply that strategy to another sample, another file that was created under the same conditions, with the same panel, with the same protocol. So something that you can compare. And you can use it as a starting point for the analysis of that sample. So once you apply that analysis strategy, you can actually activate the gating sequence for that population, and you can rearrange those gates, those regions. You can create new regions, you can change their shape, their size, you can delete them, whatever you want. So usually this analysis strategy is only used as a starting point, just to avoid a lot of work. However, even if we can say this analysis strategy that it's somehow similar to the gating strategy we can see on other softwares, it would be basically a nightmare to try to do that when we are talking about panels with 30 or 40 markers. If we take into account only the mathematics and all the combinations possible, you would see that the number of possible binary phenotypes, only taking into account negative and positive populations, would go up to hundreds or even thousands of possible phenotypes with a 40 color panel. And to do that, you would, using the typical 2D diagrams to the dot plots, you would need hundreds of diagrams to do that. And even if you save the strategy beforehand, going through the process of checking those gates because of the intersample variability would be simply a nightmare. And that's the reason why we need some kind of automatization to make the analysis process fast, reproducible, and sensitive, and taking these variability from the user's hand. In Infinisight, as you may know, we have implemented a set of automated analysis tools that were created with a clinical scenario in mind, of course. So we start with a fixed panel that wants to answer specific clinical questions. And then we employ a process that uses unsupervised hierarchical clustering to create those groups of cells that always apply over multidimensional analysis. We've tried this with raw spectral data and it works. So since we don't need to look at the expression of different markers to define those populations, it can be applied blindly over that kind of data. And then we can make an automatic labeling of the different clusters we obtain using a supervised algorithm that makes use of reference databases of phenotypes. And this is one of the things that most people don't understand. What do we understand by reference databases or analysis databases? So basically, they are collections of samples that were processed with a standard protocol with a fixed panel of reagents, well titrated, and that are somehow representative of a given sample type. For example, human peripheral blood under normal conditions, human peripheral blood from patients with a given disease, or it can be a sample from lymph nodes or peripheral blood from whatever. And those samples are somehow representative of that kind of sample, that type of sample in terms of phenotypes and the frequencies of those phenotypes. And these databases are used in different ways in the automated analysis process. They can be used simply to automatize the identification of the known phenotypes. For example, if we want to characterize a peripheral blood sample, we can automatically identify and label the normal sample populations, the normal cell populations in the blood, and leave to the user the decision about those populations or those subsets that do not have a known phenotype or a normal phenotype. So, for example, if we are looking at a sample with lymphocytosis, we can lead to the user to decide whether it is something reactive or something clonal. However, we can use these kind of databases in a tandem, and after automatically analyze those normal samples, normal populations, sorry, we can use a second database to classify those as normal cell subsets. So if we have a database of normal peripheral blood and then a database with clonal B cells from CLL, from follicular lymphoma, whatever we have in our software, we can do this tandem analysis. And this approach of using blind clustering followed by a supervised labeling with reference databases have been implemented in Infinisight for clinical applications. And those that process of clustering and labeling automatically is actually used together with tools for automated statistical analysis of the findings, quality control of the samples. For example, we can teach the software to identify, for example, contamination of a bone marrow sample with peripheral blood, or to identify some population is missing because of a reagent problem, something like that. And we can even automate the generation of final report with reference values to create the phrasing for the clinician, things like that. However, this kind of process, this kind of workflow is only possible when we can employ a high level of standardization. That's why it was well received in a clinical setting. And that kind of standardization needs to apply to the different steps of the process. It needs to apply to the protocols. We cannot simply change the position of an antibody and a fluorochrome. So we need to stick with the same panel, stick with the same reagents, or at least equivalent reagents, apply standardized protocols, have a common instrument set up for across different groups and to apply it to acquire different samples. We need to standardize the number of events we acquire to analyze, at least establishing a minimum of events based on the sensitivity we want. And something very, very important, the event rates, because something that we notice a lot is people is in a rush to acquire samples, and in the middle of the sample changes the if the cytometer allows it, changes the speed of acquisition, and it's not possible to analyze those data anymore. So this level of standardization is common and accepted in a clinical setting, but the question that I would like to leave to discussion, and that's why I said more than trying to explain what we do well or not well, it's to open the debate to whether this kind of approach, this kind of standardization and the use of reference databases of reference samples to do an automated analysis could be applied in core facilities to be employed in basic research. For example, something that comes to my mind is several groups working in animal models, in mice models of cancer, and they want to see the effect of different mutations on the tumor infiltrating leukocytes. So would it be feasible to have a common panel for all the groups to identify those infiltrating leukocytes and use these databases to standardize the analysis and share the information among the groups. So my what I want to leave on top of the table is this kind of question: is this automated data analysis something only usable in a clinical setting, or could it be adapted to basic research in a flow core? Thank you very much, and I'm open to your questions.